guess there's no one out there. Okay, so today we're very happy to have Evgenii Ievlev from University of Minnesota. He's a postdoc there, and he'll be telling us about domain walls and n=1 super angles. Go ahead.
Okay. Yeah, so I'm going to tell you about some recent work that we've done with Misha Schiffman and Shichen. Shichen is another postdoc from Minnesota. Yeah. So we're going to be working in the framework of super-Young Nielsen, 3 and 4 dimensions. So basically, as the plan, at first I will start by telling you some basic stuff that we need about the superpotential and what's domain wall in n=1 super-Young Mills, analyze it even there. Then we're gonna compactify on a circle to go into the decoupling regime and count these domain walls and analyze the domain wall effective theory. And at intermediate, we're gonna be considering the theory with the fundamental quarks added with some mass m, and then we're gonna study limit of large m, and eventually m goes to infinity. And at the end, I don't know if we have time, I will tell you also about the junctions of the domain walls, but if you don't have time, I will just skip this section. Yes. All right. So I will start with a couple of elementary slides so that would hopefully people here. And to understand the basic idea, well, let's look at this 1+1 dimensional 5⁴ theory. So on the classical level, just the real scalar field, classical, everything is classical. You can see that the basic stuff can be seen already from this model. So this is kinetic term, but just minima. So this is basically the potential, and this minima are again classically exactly degenerate. And one thing to note here in this particular instance is that well, it's a non-negative function. So I can always write non-negative function as a square of another function, and I will choose to write it as a derivative, a square of a derivative of function w, and w will be called superpotential later. But for now, you just can think of it as some function such that actual scalar potential is absolute square of the derivative of that function. In this particular instance, it's not hard to see that it's cubed. And why this function is important? Well, for once, if we are interested in minimum of this potential, since this function is non-negative, if you somehow find the zero of this function, then it's a global minimum, right? So local minimum can be even at non-zero v, but if you find the zero, v = 0, then that's a global minimum. And in terms of this w, global minimum of this v are 0 when v = 0, then derivative equals 0, then this extremal points of this function w are actually global minimum of the initial potential that we started with. Okay. Extremal points correspond to global minimum. Okay, so now let's consider a king that interpolates from one minimum to another minimum. So we write down we consider some static configuration that doesn't depend on time, only depends on space coordinate, which is called here x1, and we write down the energy functional, and you see it's sum of two squares, so you can complete it to a full square, and when you do it, you get some extra term, so which is called z here, and this extra term is a cross term between this derivative and that derivative, and you see that this cross term can be actually integrated. You see dx cancels with this dx, d5 cancels with this d5, you get just difference of this function w on the two sides. And then if you consider minimum energy configurations, then you see that your energy is a square plus some number. So minimal energy configuration is when the square is 0, because this number, well, it's just a number. It cannot be 0. Right? So then from that you obtain, by acquiring that this is 0, you obtain first order equations of motion instead of second order equation that you would normally obtain, Euler Lagrange equation. You obtain first order equations of motion, and then you, since like this is 0 and this is just some number that you can actually compute, you derive the classically exact formula for the energy of such a configuration. And on the level of picture, so you have a Kim that interpolate from vacuum minus V at vacuum phi equals V, right? So in terms of this energy functional, so this energy functional looks like a particle inverted potential, so it interpolates from one potential to another. And in the picture of this, what we're gonna call superpotential, the solution flows from one extreme point to another extreme point. Okay, so important takeaway from this is that, well, in this example, at least classically, so your potential is a square root derivative of some other function W. And if that is the case, then the energy of a solitonic configuration is determined just by taking the difference of that function W between the values in the two minima of the initial potential, right? So at least classically, if you have this so-called like superpotential, energy of your particle is determined exactly, at least classically, right? Okay. Are there any questions at this point? Okay, well, that should have been pretty simple. Okay, quantum mechanically, of course, in this simple model, there's going to be some quantum corrections. Right, but now I will start talking about bosonic series, and I will go to supersymmetric field series. And in supersymmetry, well, if you know about the theorem about like F-term non-renormalization, that's great. If you don't, just believe me that like in supersymmetry, roughly speaking, the formula for the energy that we get here, that the energy of configuration is the absolute value of the superpotential, it's like stays exact. Well, at least it's gonna stay exact in that example that I'm gonna consider here. And this quantity, which is the Z, which is the difference of superpotential in two values, between two values of the minimum, the Z is called the central charge. Okay, so now we're going to jump right into n equals 1 supersymmetric Young-Will theory, or supersymmetric QCD. So what do we have here? So usual QCD would have a gluon field and, well, say Dirac Dirac quarks, fermionic quarks, and Dirac fermion can be represented as two light fermions. That's usual QCD. So in supersymmetric QCD, we need to add spec partners for all of these particles. So for gluon, we add the white fermion, which is gluina. So gluon is obviously in a dual representation of the gauge group. Gluina also must be in the same representation. The gauge group, so A here is the, yeah, I'm sorry, there is a typo because there should be like n squared minus 1 here. Because like for instance, you have 8 gluons, right? Sorry about that. Yeah, and for each white fermion, you are required to add a complex scalar, which this is a scalar quarks. You have like two complex scalars, and you have, and this whole configuration is called the one flavor. So usually for one flavor, you would call like one Dirac flavor of quarks. For each Dirac flavor of quarks, you need actually two scalars, two complex scalars. Right, and this is called one flavor. Then we can have a certain number of flavors, and for reasons that I don't want to get into, I will consider number of flavors always less or equal number of colors. Where, and by gauge group, I will always mean SUN. So N is the number of colors in my terminology. Okay, so these two white fermions enter in a vector-like fashion with respect to current symmetry Lagrangian, but this by fragments are chiral. So they contribute to the usual Evgenii anomaly. So U1 chiral symmetry is working to Z to N, which is, so this is, but yeah, this is breaking due to Evgenii anomaly, but it's further broken down spontaneously by the gluon condensation. So you have bilinear thermal condensate, it's lambda-lambda condensate. And again, in this supersymmetric setup, this condensate can actually be computed exactly, and this formula has been checked recently by lattice computations, and is given by the lambda cube. So lambda is the usual lambda QCD, the strong coupling parameter of this symptotic gauge series. And then there is phase, and it turns out that, again, if you consider gauge group as UN, it doesn't matter how many quarks you have, like, as long as it's not larger than n. You have n possible values of this condensate. So on the complex plane of lambda lambda, we see they all lie on the circle radius lambda cube with some phase. And yeah, right. Okay, so these n values of the lambda lambda condensate actually correspond to exactly the generated ground states of this series. So this lambda lambda condensate is an ordered parameter for the parameter for this spontaneous symmetry breaking, right? So, and it can have n values, and so you have n exactly the generated ground state, and so you can have solitonic objects interpolating between these ground states. So in this simplest example, we had just like 1 + 1 dimensional sphere. You have two ground states, well, at least classical, right? So you can have solitons interpolating from one vacuum to another one. Right? First to second, or from second to first, you can have solitons. So when you leave this picture to 3 + 1 dimensions, in 1 + 1, your solitonic object was actually a particle, right? So you add 2 dimensions, so it becomes a domain wall, right? So you have like one value of lambda lambda condensate in one, your half space give another value in another half space. We have some plane, some domain wall which like separates these two regions, and I will gonna study these domain walls. And I will explain in this talk. I hope like why is it interesting and what do we get it from there. Okay, so another important thing. So remember I told you about the central charge and how the energy of your static configuration can be exactly determined, or at least classically in this example, exactly determined by a number which you can like actually compute because it like integrates, and it's just the value of the superpotential. Okay, so in this case, there is actually no superpotential, but still you can write down the central charge. So this quantity actually is playing a role of the superpotential here. And again, if you're not familiar with this, so I ask you to believe me, but that the central charge of a domain wall is actually determined by the difference of lambda lambda condensate on both sides of the wall, exactly in the same fashion as here. The energy of the solitonic configuration was determined by the difference of the superpotential in one vacuum and in another vacuum. Exactly in the same way, the tension of the domain wall, so energy per square meter of this area, is determined by the difference of the lambda condensate. So, and then you can have sort of what we call a minimal wall, which interpolates from one vacuum to the neighboring vacuum. You can also have a domain wall which interpolates from one vacuum directly to some more sort of distant vacuum. So that we call a K wall. So it is like minimal wall is K + 1, and then if you interpolate not just to the one neighboring vacuum, but 1, 2, 3, to the third vacuum, this would be a free wall, and so on as a parameter. Okay. So, okay, so now if you believe me that like, okay, you have like this many ground states, you can have domain walls interpolating between various vacua. So in this simple example, you would imagine that you would have like exactly one soliton interpolating from this vacuum to this vacuum, and exactly one anti-soliton which interpolates back. Okay. So it turns out like in this setup, this is like not quite true, because if you even constrain yourself to two particular vector, doesn't matter which two exact, but like for example, from this to this one, turns out that there are several non-equivalent domain walls interpolating between like possibly that you could possibly have interpolating between the same pair of vector, and the number of these domain walls in this minimum example is actually again n, where n is the number of colors. And to see that, let's consider the stereotypic coupling. So in this simplest example, let's say the gauge group is U2, and we have one flavor of quarks. And so if you remember, I told you that each flavor of quarks is a fermionic quark is a direct flavor, so it's two light fermions, right? So and then they entail two scalar quarks because of supersymmetry QQ tilde. So we can consider this sort of meson superfield. So it's called meson because there are two quark operator. So and turns out in my notation, Q is fundamental of the color SU2, and Q tilde is anti-fundamental, and color indices are contracted here. So this is actually a gauge invariant operator, and yeah, I will study this operator. Okay, so if you write down, yeah. So yeah, I told you that there is no superpotential. There is no superpotential for the gauge degrees of freedom. But if you add matter, then you can like write down superpotential for the matter. And in this case, if you do write down the superpotential, then the mass term would correspond to this term in your superpotential. And this is like usual classical stuff from which you get usual mass term for matter fields straightforwardly. But then there is also quantum correction, which is called affect Deisenberg or ADS superpotential, and you can derive it from just the symmetry considerations. You can also do instant computation. This is another exact result in the supersymmetric setup, which is we will take it as given. So there is another term, and you see that there is this meson operator is actually in the denominator. Okay, so classically, you would expect that for non-zero mass, minimum of your potential would be at meson equals 0, so quarks are 0. But this m in the denominator actually makes the m equals 0 sort of a repulsive point, and you can derive the extremal values of the superpotential. So if you remember, extremal values of the superpotential correspond to global minimum of the scalar potential, right? So if you take a derivative with respect to, say, m, we have small m minus lambda to the 5 divided by m squared. So you solve quadratic equation, you get to minima, exactly to minima at some non-zero m. And yeah, and this to minima actually corresponds exactly to two values of the green condensate that we have in this area. So if you remember, for gauge group SUN, you have n possible values of the green condensate in the circle. So for gauge group SU, you would expect two values of the green condensate. Indeed, that's what you have, because these quarks have. In terms of quarks, there are two vacua, and green is actually related to the quark vacuum expectation value. And what's important here is that you see that at small quark masses, the quarks actually develop large vacuum expectation values, so your theory is weakly coupled. So in this regime, you can construct a domainable solution explicitly. So you have two minima, and say in complex plane of this meson operator, you have one minimum and another minimum. And because of this m in the denominator, the origin of this complex plane of m is sort of repulsive, so you can either go in the upper plane or in the lower plane. And then, so you see you picked two vacua, well, you don't have any more vacua than two in this simplest example, and still you have two possible domain walls. They are not equivalent domain walls in this theory. You can distinguish them locally, and you can even draw a following picture. So imagine you have a domain wall, you have like one vacuum on one side of the wall, another vacuum on a different side of the wall, and you can join together two different walls. So say on the top I have like this wall, on the bottom I have this wall, then there must be some junction between these walls, because these walls are really like not the same. So in this region, that domain wall trajectory must somehow interpolate into this domain wall trajectory, but then you see it has to go through the origin, then where the theory actually becomes strongly coupled. So it's hard to construct this junction explicitly, but you see that you expect that it should exist, and you see that indeed it can have multiple degenerate domain walls. Okay, so this picture actually generalizes to arbitrary number of colors, and here I am. So I'm sweating a lot of details and tricks on the graph, but anyway, for a gauge group SUN, and this time we have n flavors of matter. This ADS superpotential actually sort of generalized to a constraint. So you have a constraint, so your meson superfield is now a matrix, so color indices are still contracted, but now since you have several flavors, you have flavor indices hanging around. And then there is a quantum constraint, so since this is basically like a product of two vectors, classically you would expect that the determinant of this matrix is zero. Actually compute it, like find out that there is a zero eigenvalue, or classically, right? But turns out that quantum mechanically, the moduli space of this matrix, or if you want, like this relation is modified, and the determinant of n is not zero anymore; it's done to QCD to some power. So, which means that appropriately rescaled eigenvalues of this matrix, product of eigenvalues of this matrix, must be 1. Okay, and then again, if I have this like from this picture, I pick two vacua. Let's say like I pick like vacuum this and vacuum that. Then I want to construct the domain wall trajectory. Then so this again the same way as quarks, they're interpolating from one vacuum to another vacuum, either up or in the down complex plane. Here, some eigenvalues can interpolate short way, and other eigenvalues can interpolate long way. But this constraint has to be satisfied like throughout all of the trajectory. And from that requirement that this constraint is satisfied, you will match the windings that the quarks pick up here and there, and you find out that actually exactly if you have a K wall, so the wall that interpolates from some vacuum to vacuum n plus K, then K moduli have to go long way, so think of it as a small number of flavors going long way and large number of flavors going short way, so that the phases match up and cancel out in this relation. But then you see that if you have n flavors, you have to pick K flavors that have to go long way, and you have the binomial coefficient number of choices to do that. So from that, roughly speaking, you can like get the sense of what the domain wall multiplicity is in this case. And this formula was like checked, and these domain walls were explicitly constructed a number of years ago, 20 years ago, I think. Yeah. In this weakly coupled scenario. Okay. Are there any questions? Right. Okay. So you can also derive a domain wall theory in this case. So yeah, it's like basic idea is that if you had n flavors of quarks, well, let's say rudely they have equal masses, then your flavor symmetry in the bulk is un. And then since you picked k flavors which have to go one way inside the wall and n minus k flavors the other way inside the wall, so you break your flavor symmetry. The wall explicitly breaks your flavor symmetry down to this one, and the quotient is roughly the domain wall theory that you get. Of course, this argument is like very naive, but you can like do checks. But like this is precisely the domain wall theory that you get, and the written index that counts the number of ground states in this area should give you domain wall multiplicity, and it indeed does. It matches with the formula I provided previously. Okay, so this is for the case with quarks. So yeah, and in the case with quarks, the domain walls are locally distinguishable because you have like some tangible matter degrees of freedom that like clearly distinguish, have different values inside the wall. So you can do, I don't know, scattering experiment or whatever to distinguish which domain wall do you have. Like, is there like a first flavor that goes this way, or first flavor of quarks goes that way, and determine that for every flavor. So you can clearly distinguish these domain walls locally. So it turns out if you start actually with pure supernegativity, with no quarks, your domain wall theory is a certain TQFT written in, and if you compactify that theory on a torus, so that the on two-dimensional torus, so that the domain wall wraps the torus as well, the ground state, the jealousy of this TQFT also should give you the number of domain walls, and it does, and it's the same number. But for example, one big difference here is that in the case with quarks, the domain walls are locally distinguishable, whereas in the case of pure supernegativity, it's just a TQFT ground state degeneracy. You cannot locally distinguish them. And what's maybe more important physically or as important is that in the case with quarks, you can have domain wall junctions like here. You can have junctions between different domain walls. It's possible, but in the case of TQFT, this is impossible. You cannot have like two different ground states of the same TQFT interpolating between each other. That's not going to happen. So, and then the question is, if you start with the weakly coupled theory with quarks of small mass, and then you increase your mass and eventually maybe send it to infinity, then you must somehow recover this scenario. But how does it happen? How does your local multiplicity turn into topological multiplicity? What happens to junctions? Yeah.
Why should I compare to the T2 ground state degeneracy specifically?
Right.
Or are you just saying it's a coincidence that you happen to look at T2, you get them like the same number?
So, yeah, so, well, if you do not compactify the number of ground states, so it's not well defined, TQFT written index is not well defined. Right? And here, yeah, I should be more precise because here well, actually, to make this situation also well defined, I need to at least slightly compactify, at least on the cylinder.
Okay, so essentially it's like, because you want to preserve SUSY. What does it really? That's why you're taking T2 as opposed to some other compact manifold?
Well, yeah, that's like one of the reasons. But, well, I guess like it's a simplest case that like, you can imagine here. Yeah, yeah, I don't know if you can have more complicated manifold to preserve for SUSY. Remember, yeah, probably not. So, in any case,
You can certainly have supersymmetry on more complicated manifolds.
yeah, but all the four supersymmetries.
Even all the four supersymmetry.
So
Still, I mean, we're asking why it had to match, and it has to match because of supersymmetry, right? But once you are on T2, there's no debate that these two have to match.
yeah. Right.
So one question. So inside the sigma model, can you construct the junction or not? Or is that outside of the reach of the EFT?
Yeah, so the junction actually looks like a kink on this sigma model.
Can you explicitly construct it or not?
You can, well, at least in the framework of this. You mean write down the profile?
Yeah.
Yeah, no. So you can write down the exact formula for the mass of the kink, but the profile itself, no, you cannot do it.
So there's a finite energy king in this theory that exists.
Yeah, they exist. Yeah. Finite energy kinks, they do exist.
Why not try to write down the profile? And the second one is just some like geodesic or something?
So, I mean, I think it might be a bit outside the applicability of EFT, the profile itself. Because you see in this simple picture, for example, quarks, when you interpolate from this wall to this wall, quarks have to go to the origin where the original gauge degrees of freedom becomes strongly coupled. But on the other hand, in the sigma model that we have on the wall, right? At least class, yeah. You can write down the kink profile there. It's classic. I don't think it would actually match to the actual quark degrees of freedom that go in the junction because it, well, from the point of view of the bulk, it must be strongly coupled region.
Well, it might be that from the point of view of the wall, it's not. But, you know.
Yeah, but then are your degrees of freedom on the wall actually match to bulk degrees of freedom that well? I mean, like you can write down a kink for the sigma model, but then if your goal is like to actually write down the so for the wall you can write down the wall solution in terms of bulk degrees of freedom, which are quarks, for example. Then if your goal is to write down the quark profile inside this junction, probably you cannot. But you can write down a solution inside the sigma model.
Right.
But yeah, I'm not sure it would match to the quark degrees of freedom. So the energy of this configuration probably would match because it's determined by this central charge. There is not much you can go wrong with that quantity. But the profile itself, I'm not sure if it would match. I don't think so. Yeah.
It doesn't have to.
Yeah, I don't think it like yeah. That's true. Yeah. Yeah. In this case, you for writing down the junction profile, this might be like outside the capability of the sigma model because it's like after all, it's to write down the sigma model. You need to basically have, for example, derivative expansion truncated up to derivatives, and it might not work out in this region, in this particular interpolation region. Yeah, so there are like some approximations that you make, which and not all of them might be actually well satisfied in this region.
So these walls are rated by a time reversal symmetry breaking, right?
No, well, or party, yeah.
Oh yeah, okay. How's that? Is there like a realization of the wall?
Yeah, I will talk about that actually later. Yeah, it's turns out to be it's a Lavoisier duality on the wall, or at least in the case of this 50. Right, okay, so now we're interested how to interpolate between these two regions. So basically we want to start with small quark mass and increase the quark mass first, like to the order of lambda QCD, and then further and eventually decouple these quarks and study what's going on. But of course, like when the quark mass is not small, when it becomes of order lambda QCD, the bulk is no longer weakly coupled, and your tools become like very much limited. So to go around this problem, we compactify on a small circle, and this area does become weakly coupled, and I will explain why. So basically, when you compactify on a small circle, so your gauge field in 4D was a 4-vector, when you compactify, it becomes a 3-vector plus a scale, right, in your effective field theory. And since the gauge field, well, it's obviously in the adjoint of a sphere, so its component along this compact direction becomes an adjoint scalar, which may develop vacuum expectation value. It turns out it does, and it breaks your SUN down to U1. So yeah, that makes the theory more tractable, and so you have one real scalar, which is the component of this gauge of 4D gauge field along the compact direction, and then the remaining U1 gauge field can be dualized into another real scalar. So you have two real scalars which combine to form a complex scalar, which is in fact part of the supersymmetry multiplet. And configurations that in 4 dimensions you would call 't-Hooft-Polякov monopoles, basically, or, well, отвлекаться these at-Hooft-Polякov monopoles, monopoles occurring due to the presence of the adjoint scalar breaking. So in 3 dimensions, these are, well, more like instantons, right? Because they do not have word line. So they're called monopole instantons. And in the same way that here quantum corrections lead to this quantum corrections to the superpotential, here monopole corrections also lead to another superpotential. And if you're familiar with say Polyakov confinement, there is a cosine potential that is generated by monopoles. Well, cosine is the sum of two exponentials, and there is also an exponential. So I think you get where the idea is coming from. Okay, so since you have these exponentials, and these exponentials are actually taken of periodic fields, so it's natural to introduce this moduli. So yeah, so yeah, roughly speaking, you can like think of them as just complex variables, but mathematically speaking, if you have a SQN is your, well, if sorry, for a gauge group, for a non-variant gauge group, you have simple rods, and then you have minus sum of all the rods, which is called the affine rod, and for each of these rods, you have different modulus. So physically, the idea is that n-1 degrees of freedom come from n-1 monopoles, which are usual monopoles. Each of them corresponds to each of these U1s. So you have n-1 ordinary monopoles, and then there is one extra monopole which has come, which actually carries 4-dimensional instanton charge. But you can think of it as the monopole coming from the fact that you secretly have on microscopic level one compact dimension. This is called KT monopole. So overall, we have n complex degrees of freedom, and surprise, as the case in the case with quarks on the quantum level, turns out that they have a constraint that the product of all these degrees of freedom must be 1. Okay, and then like there are other terms that you also can compute which all contribute to the superpotential. And again, the usual, as the usual story goes, the extreme points of this superpotential give you the ground states. So you can easily write down the ground states. And again, you can analyze the BPS domain wall trajectories, which you can construct in this case as well. Again, you have like n vacua for the gauge Europa CN, which is determined by the phases. Again, you interpolate from one vacuum to a different vacuum. Here you count like how many of these Ys can bind long way, how many short way. You will find exactly the same answer. So this, and I stress that in this instance, so we don't have any quarks. All is this, like, this slide is for super young Mills theory, and almost identical slide that we had before was for the case with quarks. So the answers are basically the same. So okay, then you might ask yourself, okay, what if like I add some number of layers of quarks? So not n quarks, not 0 quarks, but like some intermediate number. Okay, and to understand what's going on, so remember I told you that if you have no quarks, you have like that many monopoles, and these monopoles generate superpotential. Okay, what happens if you add quarks? So quarks are fundamentals under SUN. So when the SUN is broken down to U1, quarks are going to be electrically charged under this U1. And monopoles are magnetically charged. And now, because of SUSY, you have scalar quarks. Scalar quarks can develop vacuum expectation values, and they do, as turns out in this case. So, and it's a superconductor situation. In superconductor, you have condensation of electric charges, so your electric charges are screened, but magnetic charges are confined, right? You have like usual conductor, it gets compressed into a thin tube, flux tube, and the energy of this flux tube is proportional to its length. So basically the same thing happens here. If you add a number f quarks, f is the number of flavors, turns out that like f plus 1 monopoles become confined. So you can have this picture like when some number of your monopoles are connected. And this whole configuration basically acts as a molecule. It still has some leftover magnetic charge, which is like, roughly speaking, orthogonal to the electric charges of quarks that you have initially. So overall, what you end up with is that you have the same number of degrees of freedom with one, because if you started with the pure super-Young Mills, you have the n monopole degrees of freedom with one constraint that their product should be 1, and here you basically kill by confining, you kill like f degrees of freedom, but when you're adding quarks, you also add f degrees of freedom. So you add f degrees of freedom of matter, and you kill f degrees of freedom of the gauge descent, and you still have a constraint. A constraint is modified, but doesn't really matter. Like, okay, it's a constraint. Constraint is important for counting like the phases and which fields can go like clockwise, which like counterclockwise, and so on. Okay. So what is modified in this case? Since you now have mixed degrees of freedom, some of them are flavor, some of them are gauge. So it like does still like certain number of them has to go the long way, and the rest the short way. But which of them exactly go the long way? It's how many exactly flavor degrees of freedom, how many gauge degrees of freedom? It's a choice. It's a choice, and for every such choice, you have like a certain number of possible domain walls, possible trajectories, and if you sum up, very fortunately, you still get the same answer for the domain wall multiplicity. the domain of multiplicity. Okay, so what do we learn from this? We learn from this that when you compactify your theory on a cylinder, you can see explicitly flavor degrees of freedom and gauge degrees of freedom that go into your whole solution, and how much, like roughly how much multiplicity comes from each of these types of fields, from the gauge fields and from the matter fields. Yeah, and that's just a little check of all this construction is that like you can merge two domain walls, K1 walls. They, if they imagine that they form a BPS object, which is a K plus 2 wall. So naively you would expect that, okay, so there are like n of these domain walls, n of these domain walls. So you can hit a possible multiplicity of this configuration is n squared, but that I actually you need to account for the fact that these are unordered pairs, but you would still not get this right number for the multiplicity, and you have to account for the possible bindings. So in this picture, one mode cannot bind like more than once. So if one mode binds a lot, it's not a BPS, and then if you account for that, then you actually recover the correct multiplicity for K equals 2 walls. Okay. All right. So okay. So we more or less understand the theory compactified on the cylinder, affiliation, quark degrees of freedom. And now our goal is to send quark mass to infinity. Well, possibly decompactify and see what happens. And to do that, let me consider for a second the domain effective theory in the domain wall, not just the number of vacuum, not just the number of the domain walls, but the effective theory itself. So, as I said, like each domain wall solution, because you have a certain number of flavors in like one way, other number different way. So you explicitly, each wall explicitly breaks flavor symmetry, and your moduli spaces, which is the domain wall effective theory, is basically a quotient. So then you can like draw a following picture. Okay, so if you have a number of F flavors, then each wall, some of these flavors of this J is just numbers like how many of flavors of quarks should go like a long way and the rest short way. So each wall breaks the flavor symmetry down to this product. So the quotient gives you domain wall theory on when the bulk is R3 cross S1, and then if you try to decompactify and go to R4, when the bulk theory is R4, the domain wall theory becomes three-dimensional, but like nothing severe happens to this sigma model. This is a Grassmannian sigma model, which is this quotient. It's still the same Grassmannian sigma model, right? But when you repeat the same analysis for monopoles, you find that when you live on a small circle, your theory coming from the gauge degrees of freedom is still Grassmannian, but then the big question is what happens when you decompactify, because on R4 there are certainly no monopoles. And monopoles occurred because we compactified on the cylinder, we got a real scalar, which is the first component of the gauge field. That was the whole reason that the monopoles even appeared. But like when we decompactify, well, something must happen to the sigma model. So yeah, and the proposal is that like it actually turns it into a TQFT. So in this slide, so I'm not explaining here what happens actually in our case, but it's a simple example which is, well, I think, easy to digest. Like how a sigma model like, can turn into TQFT. So consider just a CP sigma model, so and As you probably know, CP sigma model can be wrote down in a linear fashion if you introduce an auxiliary gauge field with no kinetic term. With no kinetic term, if you integrate out this gauge field, you recover the original non-linear formulation of the sigma model. Okay, and if now you consider a theory which is a U1 Chern-Simons theory plus F charge scalar plus some potential, and let's say the potential at positive m squared forces at a positive m squared, so m squared is the mass of this field's n, so you can consider, imagine yourself two limits. So first is the limit when mass of this end field is large, then you can integrate them out. In this limit, this complicated thing turns into just a Chern-Simons TQFT. But if mass squared is negative, then imagine that your potential actually forces some expectation value for this scalar, which effectively acts as a constraint, and then first you can forget about the Chern-Simons factor, and then you have a TQFT. So the same theory in two different limits can look either as a sigma model or as a TQFT. So this example is a bit more involved because you also, when you decompactify, you change dimensions, because here the domain wall effective theory is two-dimensional, because one of its dimensions compactified. And here it's three-dimensional. But still, so it's like semi-qualitatively convincing argument, and it's more supported by the fact that it is actually known what is the domain wall theory when we have no quarks. So it's like a result that can be derived, for example, from string theory. Okay, so then you can like conjecture what happens when we do have quarks. Okay, so when you do have quarks, the theory that you get for monopoles on a small circle, it would be this Grossmanian sigma model. Okay, then you can ask a question like, what TQFT would it like possibly be able to convert to? So okay, so as with the CP sigma model, so CP sigma model can be rewritten in the gauge formulation. When introducing auxiliary gauge field, the same works with the Grossmanian, only you need to introduce non-abelian gauge fields. And so for this Grossmanian, there are two choices that you can actually do. Okay, so and for each of these choices, there should be some. So if you conjecture that it should be a QFT, there should be like some level assigned to it. And then if you require that level and duality should be satisfied, this actually more or less uniquely fixes your what level of that QFT should should have. Yeah, and that level and duality actually does correspond to the parity symmetry exchanging the walls in 4 dimensions, but that's some details. Okay, so in the result we get some complicated formula. The fact that you should pay attention to is that, okay, so for some number of layers, which is less than n, the domain wall theory is a product of a QFT and a sigma model. A sigma model, yeah, and you can, so when you are compactified in a small circle, you can explicitly count the number of domain wall trajectories, and in here the written index for this series, which counts the number of ground states of this effective series, well, it's actually also computable in much of the expectation. Okay, I will skip that and get to the final point. Okay, so we more or less sorted out what happens to the domain wall when you go to, well, maybe not completely decompactify, but let's go to a very large circle. Okay, so now what happens when we go to very large quark masses? So we want to analyze this area. And the basic idea is the following. So Again, at small quark masses, everything is weakly coupled. You can write down profile equations for quarks. So the wall thickness is basically determined by the quark mass. Okay, so when mass becomes large, the vacuum expectation of meson operator, if you remember, goes like there is m in the denominator. So the theory becomes strongly coupled. Quarks are very massive. Then confinement, like strong coupling, kicks in, and gluon acquire masses of order lambda. And the domain wall thickness is actually determined by the gluon mass, by like it's roughly 1 over lambda. But then, like the quarks also have to somehow interpolate inside this wall, but they're very massive. So you get the following picture. So green here is basically the like gluon coating on the main wall. Your domain wall is dominantly made of gluons, but inside there is this thin core of quarks, which somehow must interpolate, and this core is very thin. So when m goes to infinity, this core becomes thinner and thinner. If you have junction of two different walls, then roughly speaking, the gluons are the same for two walls, so you cannot locally distinguish them by just looking at gluons. But the junction is like hidden like inside, and to probe this junction and probe the domain wall, like the types of domain wall here, like as opposed to here, you need to go like high energies. You need to resolve distances of 1 over m, go to energies of higher m, but in principle you can do it. And yeah, this is a nice comment, but I don't have time to go for it unless somebody asks me a question. Okay, so this is basically the final conclusion. So we want to argue that as the bulk quark mass is varied, there is no phase transition on the wall unless quark mass is actually infinite. And like in 1 minute, this is like picture for the argument that we have. Okay, so this is a plane of 2 parameters. So we have as a parameter quark mass, and as a parameter we have a compactification scale. So L is the circumference length of a circle that we compactify it on when we consider it R3 equals S1. So CBT is like 1 over L. Right, so BT equals 0 is the 4-dimensional compactified theory. Okay, so what regions are under control? So at small masses, well, basically your theory is always under theoretical control, so you can analyze it there. At small circle compactifications, your theory is also more or less under control, and the region when M is like sort of like roughly speaking exactly infinity, so huge shipping and mills, is also well studied by some other methods. So this line is, you can say it's also under control. Okay, and then, okay, so like you can ask questions about this argument. It probably would be legitimate, but our argument is basically the following. Okay, suppose there is some kind of phase transition going on here. So there must be a phase transition line growing from that point and going somewhere into this plane. So there are a few different scenarios that we can analyze, like phase transition line ends somewhere or like goes to one of these regions, and these they are very, roughly speaking, all excluded. These are excluded because they go into the regions that are under control, and this is excluded because it's completely nuts.
Elaborate?
Huh?
Can you elaborate?
Yeah. So so the domain walls are locally distinguishable here, but not locally distinguishable here. So when you take this path, somehow you must like interpolate between these two very different regimes. How can it happen? So the only way we could make sense of it is like, again, like by looking at this picture, when this, in the event that to probe this region, you need to go to like infinite energies, then the domain-level multiplicity is not seen anymore. Or in the in other language, so if you are in like some low energy observer who has a UV cutoff that you cannot probe, and beyond which you also cannot probe, then the domain-level multiplicity like disappears when quark mass are roughly at your UV cutoff. But in principle, for any finite value of quark mass, you can still probe this interior region of the wall. It's just like you need to go to higher energies. The only point that is making sense that where what the domain-level degeneracy disappeared is when masses are infinite. Because for any finite quark masses, okay, this is a qualitative picture, but we still expect to have this like interior core of the wall made of quarks. Okay, so I think I should wrap up. So I will skip all of that stuff. Yeah. So long story short, we studied because of chiral symmetry breaking. You have in SUSY you have a number of degenerate ground state in n=1 UCD or superior wheels. So we studied the domain walls interpolating between these different ground states, counted the domain wall multiplicity, figured out like what happens when you send quark mass to infinity, how do you interpolate between local distinguishability and only topological distinguishability. We also studied actually in the paper domain wall junctions. It was like also some interesting physics, but this was like not the point of focus of this paper, so there were one or two sections devoted to it. Thank you for your attention. Right. So
Could compare your result with Bertolini last slide.
yeah. Okay, so in this paper, again, in this paper, the authors basically started with generalizing a Cherev-alpha construction on string theory. So they generalize it to the case with flavors in order to make a guess what the domain-level theory is, right? So if you accept that, so the domain-level theory is basically some three-dimensional theory with that superpotential. So there is a mass term, there is like quartic terms, the superpotential, and then okay, so taking this as our new starting point. Okay, so there is like some fixed parameter alpha, and then there is a parameter of mass dimension m. You can analyze, okay, what is the vacuum structure of that theory depending on this value of m. Okay, and they find that naturally when mass is positive, you have no symmetry breaking. When mass is negative, you have spontaneous symmetry breaking. But yeah, another following picture. Okay, so some small masses, spontaneous symmetry breaking on the domain wall theory, and vacuum of the domain wall theory correspond to the different domain walls from the point of view of the bulk, right? So you have like some sigma model. This domain was locally distinguishable, but there is no symmetry breaking. Then, like from the point of view of the bulk, domain walls are not distinguishable locally. In fact, if you compactify, say, on a torus, you see that there is like some TQFT degeneracy. Okay, so that happens when this three-dimensional mass is equal to 0, the transition, right? But then, like, there is no way you can like reliably compute relation between this three-dimensional mass and that four-dimensional. Okay, so you can like still make a guess, and they may make a guess like that m equals 0 on the wall corresponds to some finite quark mass in the bulk. I agree that this is like sort of a natural guess. Well, it's not sort of, it is a natural guess. But our results suggest, otherwise our results suggest that this is actually equals to infinity. Or if you are low energy observer that is constrained by some UV scale, then when that mass is that your UV scale, roughly speaking. So that's basically all I can say about that paper. So we kind of like disagree with this paper on that point, but the domain, but if you like take everything like all the results of that paper like below that point, like the degeneracy, the actual domain wall theory, it all like agrees. Well, I mean, like we agree with these results. We derive them in like, I think, completely different way. And this is nice, like the double checking things. And we disagree on the location of that transition.
So take the guess and they don't disallow for infinity.
Well, they say that okay, it's like probably some finite value of quark mass. So, and all their like subsequent argument is made under the assumption it's some finite value, because like if it's infinite, then you don't have this region anymore, right? But they do have this region to the right.
So which way do you control the QoS by n? You just increase the circle size.
So, well, some information about this region comes just from stringy constructions, because, well, when you have flavors, there are like some complications, but when you don't have flavors, it's, yeah, you. So I guess like you're asking why do I even have some regime when this like theory is under control, right? So in stringy construction, like you have also like parameters like alpha prime, and you construct. I'm not an expert on that, but from what I understand is that you construct a certain brain intersection configuration. That like on the intersection of brains there is like your four-dimensional Young-Mills theory, and then there is a regime in string theory when it is weakly coupled, and you can like obtain some results. And then there is a regime when the theory on the domain wall intersections is actually your Young-Mills, and these might be different regimes, like different values of that stringy parameter, right? But you can like make a guess, okay, so nothing bad happens when you interpolate from, in terms of that parameter from one region to another. And so you like make a guess, okay, so like this and that result like, probably still holds true in both of these regimes, so you can compute them in weakly coupled string theory and then extend them to the theory that you're actually interested in. Yeah.
Also, it's not as controlled as the like small circle and the small hit space.
Well, there are also like a lot of qualitative and admittedly iffy statements that I made in this talk as well. So I wouldn't say that like my approach is like better than this approach. But in that like arbitrariness sense, but like, we try to do the arbitrary mass. That was our goal. So.
What is the one thing with the M double star there?
Right. M double star. Okay, so yeah, then you might start asking questions. Okay, so in pure Fourier Young-Mills, the theory on the wall is like TQFT, right? So, but there is this thing called what's it called? So anyway, yeah, and this TQFT is related to the one from center symmetry that you have in the bulk. So, in principle, when you have quarks, which are in fundamental quarks explicitly break one from symmetry. But generically, you would expect that, like, if you introduce very heavy quarks, that your one-form symmetry might still emerge in the IR as an accidental symmetry. But at least up to the point when quarks are sufficiently heavy. So beyond, if your quarks are lighter than this supposed value m star, then your one-form symmetry does not even emerge in the IR. It's just never there. So, well, roughly speaking, the idea is that, like, when your quarks are sufficiently heavy, then, like, at low energies, you still have, so your gauge group is still confining. It's, like, not severely broken, and still have enough strong coupling dynamics to, well, roughly speaking, to account for this one-form symmetry. But if your quarks are very light, then because of ADS potential, gauge group is broken very badly, right? So there is no room for that. Okay, so then the point is that this one-form symmetry should live on some finite length interval. I mean, not finite length interval, but it actually should start at some finite point, which extends to infinity, right? And then, yeah, well, we tried to make sense of it, and, like, it looks like the Chern-Simons QFT that, like, is living on the wall is related to that one-form symmetry should also live in that finite length interval. So it might be that the so roughly speaking, this is the region where the yeah, maybe I'm saying stupid things, but the sigma model, quark sigma model on the wall probably coexist at least in some region of energies with the Chern-Simons theory in this region, but at least in some intermediate region of energies. Yeah. And there was another point in our paper that if you have one-form symmetry, like the center symmetry, then actually it doesn't extend to this plane. So if you have arbitrarily small circle compactification and arbitrarily large but finite quark mass at the same time, it just, like, it's broken immediately. Yeah, and that flavor that we studied here. So this phase transition is, well, roughly speaking, it's if you remember, the main wall breaks flavor symmetry. So this is a phase transition with respect to spontaneous flavor symmetry breaking on the wall, and it's a zero-form symmetry. So we expect that there should be, like, some lines extending into the display going from that point, but not from that point. That's what I can comment on this post about that picture.
Maybe we should thank Evgenii again.